And let us begin with our first physics recap of the year this year. In this series, I present 5 papers that were published in the previous month, and I try to extract some concepts from them so we can both learn and see what physics has actually been doing on a level hopefully more technical than what the news outlets are saying. Keyword is hopefully. We have a format now, a completely arbitrary one, but a format nonetheless. There's going to be 3 papers from journals and 2 from ArcSiv. Of those, 1 journal paper on theoretical findings, 1 journal paper on experimental findings, and 1 on applications and or things you wouldn't typically look at as physics, but hey, it was published in a physics journal, so leave me alone. 1 ArcSiv paper that I personally find interesting, and 1 ArcSiv paper that I don't, but I still learned something from, probably. Also, do not come at me in the comments for saying ArcSiv as ArcSiv. If I said it as archive, you wouldn't know what I'm talking about. I'm introducing this format now to clear up some things that I didn't really like doing in the previous video slash the test run, and those are the further questions. I felt like there was only so much I could say for why I selected this paper, and hopefully introducing these categories right off the bat will be insightful. It sure was for me when I was selecting the papers. Um, let's see. Now, for the usual disclaimers, I am not an expert. I just like to read, think about, talk about research. So if you're more knowledgeable than me, then I would appreciate any corrections that you may have. If you notice something wrong, please comment it. I will have a dedicated section for corrections in the description because we're all here to learn after all. Um, anyways, yapping out of the way. I will have some important announcements at the end of the video, so I encourage you, even if you don't actually care about the papers, which, come on, first of all, to at least skip to that. There will be a timestamp slash chapter called End Matter, and maybe a separate video if I decide to break this up into videos. Thank you. Also, I'm a YouTuber now. Like and subscribe if you like the format or my face, I guess. I don't really mind. I am a girl on the internet after all. Let us get started with the theory paper. This one is very theoretical, I'll admit that, and I should probably read the title. Nonlinear Oscillations of Strings and Beams by Philip Fischek and Maciej Maliborski. Maybe. I'm so sorry if I'm butchering that. But yeah, by these 2 people. And again, I'll admit that this paper is very theoretical. It talks about specific classes of solutions to a particular equation, specifically a defocusing cubic nonlinear equation. Try saying that 5 times fast. In any case, as you may glean from the title of this paper, it talks about um, oscillations in the solutions to like string and beam problems. These 2 are lumped together because even though physically they may seem very different, right? Like a string is all bendy and squishy, while a beam in the daily sense is quite rigid. Mathematically, these situations are quite the same. We have some medium, right? A string, a beam, a fluid, perhaps like some kind of field, and we have oscillations in that field. And this is modeled by the above mentioned equation, which you can see on the left of this slide here. This paper shows that the solutions to these problems are related to each other in an almost fractal-like way, which is fascinating. And it also adapts a technique from another paper, which I will also talk about to simplify and explain these fractal-like relations between the solutions through so-called reducible solutions, which are ones that can be modeled exactly. Not only that, but some solutions are verified to be stable, which means they may actually have meaningful physical contributions to these beam and string slash wave solutions, right? And as you will see in the final question section, which I'm not completely getting rid of, there may be other applications as well, like I teased with fields. And if you want to think about what those applications might be more concretely, I have put up these equations and the boundary conditions on screen. Yeah, if you want to think about that while I talk, that'd be Interesting, maybe. Also, the defocusing in defocusing cubic nonlinear equation thing is because there's a plus sign in that equation, so it's repulsive. Sorry, equation I've seen prettier. Anyways, there are many interesting mathematical techniques employed in this paper. I'll try to go through them one by one, but I would like to preface this by saying I'm not here to teach you any of these techniques. This is just background information which you may need to understand the significance of this paper, and I am primarily relying on the references within the paper itself, as well as the actual paper. Um, so I would like to begin by explaining the Galerkin scheme used throughout by introducing a simplified reducible system as described in the paper. This example was used to illustrate the existence of solutions with higher energy, despite having roughly the same period of oscillation or frequency of oscillation, as you can see with this plot shown right here. I'll go more in depth into this later, but you may observe these branches from the main curve in figure 2 right here, for example, right? These branches are at the heart of the fractal-like structure of the solution space. So the general approach to working with an ansatz assumption for a form of the solution is basically to chuck it into the equation and see what happens, right? And here, this is the ansatz we're using. Um, More generally, there will be more terms as we will see later, assuming I've put it up on the slides, but if not, we can just look at the paper in my browser. So yeah. In this problem, a technique called the Galerkin scheme for numerical approximations is used to further help in solving this generally non-integrable system, right? This is actually quite similar to a Fourier transform in that some basis functions are taken and added together with some coefficients, right? Stuff like that. And this is where we get this system of equations from, as the whole point of the Galerkin scheme is to simplify partial differential equations into some set of linear equations. It looks scary, but a good analogy is finding the equation for a like for a quadratic by looking at a graph of it, finding things like the vertex and x-intercepts, which is quite similar to what you may see over here. I got this from, I think, a textbook, but I will have the credits for all of these images linked in the description, so you will be able to find that that there as well. Let's see. And in fact, the Galerkin scheme seems to be typically done using polynomials, but since we're looking specifically for periodic solutions, so the oscillations, sines and cosines are used. Also, this kind of system for non-reducible cases is much scarier. So, you know, you win some, you lose some, I guess. It's scary, but the actual problem's scarier. I don't know why I worded it like that. And this is the equation that we're chucking it into, the defocusing nonlinear cubic equation, I think it's called. Again, try saying that 5 times fast. Um, okay, so why did we do all of this? Well, I'm going to jump ahead a little bit and explain figure 4 because it is the reason we did all of these things is to analyze the simplified system. Uh, Here it shows stability and instability of certain combinations of energy and how much the fundamental mode of oscillation contributes, or basically what its amplitude is, right? And note that this lower panel is not like just a zoomed in version of the higher panel. Um, the axis of energy is the same across here and here, the x-axis of energy, but here it is the frequency, and here it is how much the fundamental mode of oscillation contributes. This figure is crucial to understanding the fractal structure of the solution space, where there is no fundamental mode contributing. Let's see. Yeah, when there's no fundamental mode contributing, this graph has an x-intercept, and that's where a new trunk forms, right? So this blue line right here is the trunk, and these red parts are called branches, right? Since, as stated by the paper. Now, all of the intercepts here, I'd wager most intercepts generally are going to be unstable. And this makes sense because these branches have a higher energy, which needs to go somewhere, right? Which means the trunks of these branches are also going to be mostly unstable. Why um why I say mostly is because the paper actually makes a point to basically justify itself by saying there are some stable solutions in this branching structure which can have a meaningful physical contribution. An instructive point looking at the second panel here is you may notice that there is a certain symmetry in stable and unstable solutions, right? Like right here, half of this is stable, the other half is unstable. Um, Here as well, I don't know if you can see my cursor, so let me just draw it then, right? Like this part here is stable. This part here is stable. This part here is stable, and that kind of has almost like a symmetry with these unstable parts. Yeah, okay. And the symmetry brings us to our next point, which is flow K theory. The basic premise of this theory is to express periodic motion, in this case the oscillations, as two components, the actual periodicity and some function which governs the amplitude. Typically, for stability analysis, the latter is an exponential function. This is the key point. If the exponent is negative or exactly 1, the solution is stable, whereas if it is positive, the amplitude will keep growing and eventually go to infinity. While this is the basic premise, how it's applied in the paper requires a separate explanation. If you've ever worked with Hamiltonian systems, you may be familiar with the concept of phase space. You may also be aware of Liouville's theorem, which basically says if a fluid flowed according to these vectors in phase space, then it would be incompressible. From this follows what the paper states, that for every eigenvalue, that implies the amplitude must go to infinity. Let's see. Let's go to infinity. There exists another that implies it would go to 0, right? As you can see from this excerpt right here. Hence, the only real stable solutions are the ones for which the amplitude stays exactly constant. The above correspondence is also, from what I can tell, the reason why we saw the symmetry between stable and unstable solutions in figure 4. But again, if that is not the case and you know that, and you know why that is not the case, please comment. Next up are the figures. I think most of them are self-explanatory from what I have already presented, so I'll just talk through them to make this coverage more full. Figure 1 shows one main solution trunk in the black, which was the one analyzed in previous work by these authors to understand the trunk and branches structure, as well as to understand bifurcation in this structure. Now, you may hear bi and think 2 of something, and granted, you would be partially correct. More generally, however, bifurcations are when something, in this case the solution space, exhibits some qualitative change without any quantitative change. In the case of this system, this would be the fact that there are loops. And it's easy to trace this graph with your eyes as being loops. For example, right here, actually I have a zoomed in version somewhere. Yeah, right here, as being loops. But what we actually see is that one energy can correspond to two frequencies for the oscillation. And in this sense, you would be correct to interpret bifurcations to mean 2 of something. Another important feature of figure 1 are the thinner gray lines representing what I talked about above, unstable solution curves which extend out from the loops of the initial curve. You may notice these gray curves all look very similar to each other, and this is no coincidence. They are actually rescaled versions of the original black curve. I'm not actually sure by what factor, however, perhaps the frequency of the new mode. In any case, this rescaling brings us nicely to our next point, which is figure 2. This figure shows how branches get added as we start to resolve finer and finer details using the Galerkin scheme. If you remember, the ansatz we were using for the reducible system had two terms, but in reality, the ansatz actually includes a sum of sines and cosines of sine and cosine modes, with n being the specific number of basically these terms, right? So as n increases, more branches and unstable modes are present. This is also why the paper describes the overall trunk plus branch structure as like a Cantor set. Granted, I do not have the understanding of set theory nor the ability to precisely visualize what the authors mean by Cantor-like set, but my understanding is that these branches may get as close together as their thickness allows, quote unquote thickness, right? Without actually touching each other in the arbitrary closeness sense of the word. This is what also allows us to describe these curves as fractal-like, because the Cantor set is itself self-similar. Also, do not quote me on my explanation here, because frankly, defining it like that confuses even me, since the rescaling symmetry used to get the additional stable trunks from these branches in figure 1 should admit any rescaling. So why wouldn't it get arbitrarily close? I'm not sure, but I digress. Actually, no, I don't, because I think it may be tempting to look at this whole figure and try to take n to infinity. And if you were tempted to try that, then congrats, because that's exactly what the authors tried in a separate paper, giving reason to believe that fractal-like patterns exist or persist as n goes to infinity. So that's pretty cool. In the next figure, figure 3, it invites us to look closer at a single branch, which is what I showed earlier. It also notes down the various regions and overall gives us a closer understanding of what is going on, which we could not have seen in the above figures because they were just too small. What is most what is most interesting about figure 3, however, are these panels on the right. Now, unfortunately, the paper itself does not discuss these, but I don't have much to work with, but I will try my best. It is fascinating after all. I mean, look at them. They look kind of like evil eyes, because these actually physically show how the system oscillates in time. Red here means positive, and blue means negative. Tau here is the period, and x is how far along some hypothetical string beam, etc., the motion occurs. This makes for some pretty cool colors, as you can see. And if you just look at a thin section of this figure, let me draw again, you'll be able to understand the physical scenario we are working with. So I don't know, let's take panel, I don't know, which panel should we take? Let's take panel C. And let's draw some axes. Wow, that is a perfectly straight line. Um, so let's say this represents the deepest red, and this right here represents the deepest blue for figure C. And let's say we take this slice right here, right through the middle. Right? That seems like a good slice. We will see that the physical scenario looks something like, and forgive me, I will not use the colors because it will just be a pain to switch between all of them. We will see something like this. And then of equal width to what I drew here, but not fully reaching the deepest red possible. And then back down to the deepest blue possible. This is the physical, and it should be a little bit thinner. Something like this, right? The physical scenario. And again, it's probably not going to be like these exact sine waves because these are nonlinear oscillations, but this should give you the general idea for what we're working with, especially considering the paper does not give us this, right? Unfortunately. Let's see. Hmm, why didn't it clear? Okay. Anyways, back to figure 4 for a sec. This one looks at the stability of various solutions, as I mentioned, laying out that the branches are unstable. The bottom graphs here show how much of the fundamental frequency corresponding to the trunk contributes to the overall oscillation within these branches. Yeah. Um, the what? Okay. You will notice that the areas that are shaded red to mean unstable are the ones closer to zero, and this makes sense, accounting for the fact that these areas represent the branches, right? When the system has higher energy, that's off the main trunk. That's because oscillation modes that correspond to this higher energy are contributing, effectively pushing out the fundamental mode. And I think that's pretty neat. Also, there are areas on the trunk itself which are unstable. Oh, we can zoom in. That's nice. Right here, for example, a little bit off of this branch is unstable. And this is what makes the left graph not as symmetric as the right graph, although you can still kind of see this section at the start here. Yeah, even though the basic principle from flow K theory still remains. And lastly, we have figure 5. We don't have figure 5, which shows stability. Okay, that's okay. Um, you can look at figure 5 yourself. It really just also showed stability, and there wasn't much to discuss. Anyways, I was just gonna tell you to stare at it. So anyways, I know that was a whole lot of rambling, it may seem, and with it being the theory paper, like it seems that this is just physicists playing with equations, which of course has merits of its own. That being said, there are applications mentioned in the paper, field theories being the most interesting to me, but also things like suspension bridges and, if I manage to pronounce it, nano-electromechanical systems. Also, just let the physicists play with equations. They've earned it. And for the further directions of research, if you will indulge me, I want to get a little bit philosophical first. When I was first learning physics, I thought the goal was to be able to analyze everything equally and at the highest level, which is why I honestly felt a bit uneasy reading this paper because it goes against that. However, I now understand that there are limitations to maths, integrability being the most prominent one for this system. But some problems really do deserve more attention than others. The people behind the Cacio e Pepe paper would disagree, but and oftentimes what you might find in this kind of theoretical work is not that different from any other problem solving, which is why I personally found this paper so fascinating and accessible in terms of understanding. Anyways, there have been quite a few papers in the series discussing the system, and while I don't think the results described here need to be verified experimentally in the traditional sense, as they are more of a caution, I do see this paper's conclusions being used and applied in, for example, engineering, even broader than what I mentioned with suspension bridges and nano-electromechanical systems. Nice. The next paper, quantum vortices leave a macroscopic signature in the thermal background by Luca Galantucci, Giorgio Krstulovic, and Carlo F. Baranchi. I'm so sorry. Talks about helium, specifically liquid helium, which only occurs at temperatures of about negative 269, nice, Celsius or 4 Kelvin. In English, this is like really cold. At temperatures this cold, the individual atoms within the superfluid form something similar to a Bose-Einstein condensate. Within the superfluid? No, within the helium. You don't know what a superfluid is yet, and that's okay. But yeah, they form something close to a Bose-Einstein condensate, occupying the exact same quantum state and behaving as one large quantum object. However, the actual dynamics of things like heat flow in liquid helium, the specific phenomenon is called thermal counterflow, reveal that the helium actually behaves as two separate fluids. One is the superfluid, and one is the normal fluid, which behaves like any normal everyday fluid with some non-zero viscosity, whereas the superfluid has zero viscosity. And this separation occurs because the superfluid, once again, occupies the lowest possible quantum state and exhibits macroscopic quantum phenomena. So yes, the viscous normal fluid, yes, that's actually what it's called, exists due to thermal excitations, which, due to something with how the superfluid breaks its quantumness, get allocated to the normal fluid effectively. Now, as stated in the paper, much of the work going into liquid helium research has been dedicated to the superfluid rather than the normal fluid. This paper changes that by looking at how the vortices, which occur when the fluid is heated from some direction, can be observed and detected at macroscopic scales. Which is super cool. Um, Macroscopic scales. This paper finds that these vortices leave so-called wakes, which propagate out from the individual vortices and can be detected potentially using such sophisticated techniques as, from what I can tell, putting a particle in the fluid and seeing where it goes. This paper also talks about mutual friction between the two fluids, which is what forms these wakes effectively, as well as turbulence in the thermal counterflow when these wakes cross each other. I think this is pretty cool since it means both the superfluid, by exhibiting macroscopic quantum phenomena, and the normal fluid, through the wakes, exhibit wave interference. So that's cool. Um, there frankly isn't much to talk about in this next section for concepts. Primarily, this is because not a lot seems to be known about the concepts needed to understand this paper, but I will try my best with the sources I do have. I'm making both educated and uneducated guesses. Disclaimer precedes this whole section, and I encourage you to read the literature. The concepts here will deal in some way with rotation. To start that off, let's talk about entropy, which is like entropy but related to the transition from laminar to turbulent flow. You may have already seen demonstrations of laminar flow online, water that looks like it's not even moving because while it flows very steadily. Turbulent flow is the opposite of that and should be more familiar because most fluid flow is turbulent in your daily life. Water from the faucet, for example, whose flow you can clearly see, intuitively speaking, it can be understood as turbulent flow because it is more chaotic and disordered than laminar flow. A similar observations to when entropy may have been first presented to you, right? As for where the rotation comes in, I am extrapolating from an extrapolation made in the stack exchange answer here, so again, bear with me. As you may see in this simulation from Wikipedia, turbulent flow can be characterized by these vortex-like shapes. Entropy is a measure of the overall vorticity of a fluid. It's a bit more complicated because it takes the vorticity squared. I think that's just so that clockwise and counterclockwise don't cancel, but the gist of it is that more spinny and the more chaotic the flow gets, the higher the vorticity and entropy will be. This is just an image that I plucked from the internet when I searched entropy. It's pretty chaotic. And also there's a little heart here, which I just noticed. That's cute. Next, vortices and vortex lines. These aren't really anything complicated conceptually, simply lines of the centers of rotation in the fluid. From what I can tell, vortices don't just arise out of nothing, though. One must either rotate the fluid, introduce some kind of topology to it, or, according to the paper, introduce thermal counterflow, which is literally just heating the fluid from a particular direction, and then the structure of the liquid helium, the superfluid helium, will do the rest. And as mentioned before, this is when the superfluid carries heat towards the heat source, whereas the normal fluid carries heat away from it. Unintuitive, but it is a thing that happens. In any case, all that really matters for the next point is that these vortices exist, and also they look cool. I'll show you later. The next point is quasiparticles. If you remember from the Nobel Prize video, quasiparticles are some excitations that behave like particles and are convenient to model as particles mathematically, but are not fundamental particles. There's three types of these within superfluid helium. Phonons, which is this straight slope right here, rotons, which live in this dip here, and maxons, which are less relevant. Sorry, maxons, but you're not even mentioned in the paper. Anyways, phonons behave similar to sound waves in any ordinary material. Rotons, on the other hand, give us two things: a segue into explaining mutual friction and an absolute headache. Indeed, rotons are very uh, poorly understood on the microscopic how level. However, I can give you the what with the aid of this graph once again. This shows the relation of how energy is propagated or dissipated by these quasiparticles, basically how they move. In the leftmost portion are the phonons, right? And they dissipate slash move linearly, once again, similar to sound waves. Rotons, on the other hand, exist in this dip, as I mentioned, and they have some interesting properties. First of all, they have momentum without dissipating any energy if they live at the very bottom of this dip here. And this is called a mass gap or energy gap. I don't know. I feel like I've seen both things, both terms used. I haven't been able to figure out exactly why they have this mass gap, energy gap, or where the energy goes, but from but my guess, given context clues and the name, is angular momentum. This would also explain the next oddity, which is the fact that for this downward sloping region on the left, right, the rotons are minus. The rotons move in the opposite direction from their momentum, which is weird. And might not be as weird if you're familiar with something like spin and particle physics, but it's still really weird considering these aren't fundamental particles. So it should be possible to model them, if not with classical mechanics, then at least with something we already know, hopefully. Um, there are also a type of rotons that behave more like a phonon in that it travels in the same direction as its momentum. Again, I'm aware this seems complicated and unintuitive, but the reason I'm presenting it is because it allows for a nice description and a nice segue into mutual friction. So, back to vortices for a sec. When a roton encounters a vortex, depending on what kind of roton it is, right, R minus, which is the weird ones that move in the opposite direction to their momentum, or an R plus one, which are more normal, and also depending on the way which the vortex is spinning, it will either be deflected backwards completely or deflected only slightly to the side, effectively forward, as you can see with this line right here. By analyzing the scattering, and in fact it is referred to as scattering in the literature, we can begin to understand properties of the medium, such as mutual friction, because mutual friction is directly related to the vortice's behavior, right? And this is because there is an assumption that liquid helium has these no-slip conditions, meaning that the fluid does not slip along the sides of its container as if it were, for example, a slab, right? It kind of just flows like a fluid. You don't say. This is important and a common assumption in field dynamics and also gives us mutual friction in order to balance out something called the Magnus force, not named after the chess grandmaster, which acts on the vortices. This force is what curves the motion of spinning objects, and you can even observe this in your daily life. If you, for example, ever thrown a curved ball, as you can see here, Frisbee or even a bowling ball's motion operates on this kind of principle. Because this curving cannot allow the fluid to slip, a friction must balance it out, and this is precisely what is called mutual friction. This friction is also what allows the normal fluid and superfluid to interact with each other. And as you can see, this is just a diagram of thermal counterflow that I plucked somewhere from the internet. A few. Okay. Figure 1 is very pretty. Very pretty. It shows vortex tangles. It shows for some parameters listed below the figure, right? Temperature of 1.5 Kelvin and two different counterflow velocities. Remember, counterflow is thermal counterflow, and the vortices arise due to thermal excitations. They are in the normal fluid after all. Hence, it should come as no surprise that at higher temperatures, there are way more vortex lines or tangles, hence making the flow more turbulent. Okay, that's it. This is all you get. The next two diagrams are arguably the least visually interesting in the entire video, so that's cool. In figure 2, we have two panels which show the probability distributions of velocities for streamwise or along the direction of the heat flow, right? In here, it's horizontally, or spanwise, which is perpendicular to the direction of heat flow. In the case of this diagram here, it would be upwards and downwards. A biprobability distribution is just meant how many particles have a certain velocity, normalized by the total number of particles. As you can see, for spanwise, there is significantly more variation in the velocities, with broad tails to the left and right, whereas only to the left in the streamwise panel. It also makes sense that as the counterflow is increased, aka as the temperature is increased, and hence there's more energy for more thermal excitations, the variation becomes larger and the graphs more spread out. This is simply because more things can happen in the fluid, which may potentially affect the velocity, as discussed, for example, in the context of quantum vortices. And this is figure 3. All right, I've edged y'all enough. Time to look at the actual vortices, specifically the wakes, which they form as shown in this figure. The setup is very important to understand. The thermal counterflow goes along the direction of this ruler indicated in the figure's description somewhere. These wakes, as with wakes in water from, for example, dropping in a pebble, describe how the velocity of the normal fluid changes around the vortex as it moves. This probably has something to do with the Magnus force, I would assume. And in fact, if you look up an image of like the aerodynamics when you throw a curveball, I feel like it would look similar to this and you could draw a parallel there, but unfortunately I did not put it up here. Oh well. Anyways, the panels next to this figure correspond to most of the same things as what was already shown above. In the streamwise or parallel z direction, there's not much upwards variation in the velocity, while in the spanwise/perpendicular x directions, there is a great deal of variation. Now, I would say this is a similar picture to what I described earlier with the scattering of protons, but I'm actually not sure how to connect it, since wouldn't it mean that the incident protons would have to be in these blue regions of higher velocity? Perhaps there is something to do with the nonlinear nature of protons, or perhaps I am completely misreading this diagram. I'm frankly not even sure why the incident and scattered particles would have to be in the blue regions. If anything, it's possible that the slower velocity is exactly what corresponds to the mutual friction, which as I mentioned is connected to protons due to scattering. However, I would appreciate like any clarity or any corrections in the comments. In any case, this is some very visually interesting physics. Figure 4 also exists. It shows what one would have to look for experimentally. If you want to, you can pause here and just stare at it for a while, I guess, but I believe everything to be explained has already been explained for figure 3, which is why I'll be moving on to the further questions now. So what does this paper change? As stated by the paper, most of the research going into liquid helium has concerned the superfluid part. This paper not only looks into the normal fluid, but its results could also help experimentally confirm some of the theories relating to the microscopic structure of the fluid, which were previously too small for current techniques. Not only that, but superfluid helium has found some applications in accelerator engineering, as evidenced by a document published by CERN concerning, pun absolutely intended, are you kidding me? The cooling of superconductors in these accelerators. The link to this document will be in the description, assuming I don't forget. So for further directions of research, not much is to be said, at least not anything that I haven't just discussed. Of course, as with anything, it's important to reproduce results, tweak parameters, and verify things experimentally. Of what this paper does mention is a potential link to quote unquote thermodynamic phenomena, which links to a closed source paper that doesn't mention much of thermodynamics directly in its abstract, so I'm not sure what that could be. That being said, my lack of ideas doesn't come from a dead end. It comes from the fact that this study of normal fluid does seem to be in its infancy comparatively. Hence, I do believe many things can come of this, as briefly mentioned in the summary of this paper. And I would be very interested to read more about how these wakes may overlap with wave interferences in the superfluid. My very uneducated guess is that would produce some very visually interesting physics. But either way, cool stuff. Paper 3 is the applications, and frankly, I am still a bit surprised that this paper is considered physics. Mostly because there's a lot of biology involved as well, and I'm scared of biology. You may already have figured out that this is the applications paper, even if I didn't say that this was the applications paper. And it is titled A Polyhedral Structure Concerns Controls Programmable programmable, okay, I'm redoing that. A polyhedral structure controls programmable self-assembly by Maximilian C. Hummel, Thomas E. Wiedebeck. Wow, these names are not giving me any break today. Daiichi Hayakawa, W. Benjamin Rogers, and Carl P. Goodrich. Carl. I'm so sorry. So yes, this paper talks about the rules and framework behind how small particles come together to form larger structures and how it is possible to influence which structures are formed by changing various parameters about the interactions between these particles. This is all summarized as a polyhedron in parameter space. Now, you may be asking what are the parameters? Well, the binding energies of each of the sides of these particles to other particles and also themselves. I feel like I should have included figure 1 here. I feel like I should have. I'll be right back. Okay, so this is figure 1. I covered up a bit of the abstract, but honestly, who needs an abstract when you can just have yours truly yapping in your ear about the paper, right? And these are the binding rules that I mentioned, how much a particular side binds to other sides is governed by these parameters. So that's cool. Let's see. Oh yeah, and the concentrations of each particles are also taken into account, as you can see in panel B. What this paper does is determine for which concentrations and binding energies are certain structures designable, aka can they be formed with 100% yield. These are the sides of the polyhedron, which we will take a closer look at later. Let's see. The sides of this polyhedron right here, we'll get to it. It's in the slideshow. We'll get to it. However, most structures won't be designable. Intuitively, this is because they are some stepping stone structures to form, which, for whatever reasons, may not all come together when we are trying to form the target structure, right? So this rhombus kind of looks a bit like this hexagon structure or this triangle structure, which means that this rhombus will not be designable as you will be able to see later. And this, whatever reason, I think has something to do with the entropy of the system as discussed in reference 27. The results of reference 27 are actually very important for what this paper does. See, before this paper, most of the work going into this field of self-assembly was concerned with how to optimize the particle types and their binding rules for the highest possible yield. This paper takes that concept and adds way more ways to optimize for desired or target structures. That being said, this paper also acknowledges not all structures are designable and uses the polyhedron framework to maximize the yield of these non-designable structures relative to structures which necessarily must also be synthesized alongside them. These structures, which must appear alongside the desired target structure, are also called necessary chimeras, and I am saying that purely so I can put an image of Casaneteto into this slide. I went a bit insane while scripting this. So, as I mentioned, already, this paper cites extensively to reference 27. This is because reference 27 provides an algorithm for enumerating all of the structures which can be formed by a certain set of rules. For example, these rules, these binding rules right here. This does not, reference 27 does not yet take into account what the paper we are discussing talks about, that being concentrations. The algorithm instead gives us all possible structures for a given set of binding rules. Now, I am a computer science girly, so I feel a bit obligated to talk about this research. The algorithm works by repeatedly adding and removing particles from any given structure, and importantly, if there are multiple ways that a particle can bind to another, the algorithm ensures that duplicates which visually do not look different are ignored. This is noted in the reference as the function to add particles to a structure, depending only on its topology. Unfortunately, since I don't have access to the supplementary material, reading this reference on Arxiv, I cannot confirm that's how they're defining topology here, so my above explanation is an educated guess. The rest of this reference works to confirm that this approach, where we have only a few types of particles, this is called semi-addressability, actually has yield advantages over full addressability, where we can control exactly where every particle binds. Not to mention, full addressability is less economical and does not allow for modifying the structure after it has been assembled in the same way that semi-addressability does. I would also like to talk about DNA origami. Although I am firmly not a biology girly, as I said, biology scares me, which means there won't be much explaining going on. I do want to point out what I have been able to gather from my research. So, DNA origami uses single-stranded DNA. From what I can tell, this is different from RNA in that it's more chemically reactive, which is useful for the origami part. As you may know, DNA consists of T, A, C, and G components. Do not even ask me to try to pronounce the full names, okay? Okay. T binds to A, C to G, as you can see in this diagram right here. This binding is also what? Yeah, this binding is also what allows for complicated structures to be assembled, specifically along scaffold strand of DNA whose structure is well studied and has many smaller strands, like you can see here, attached to it in solution. The origami part comes in after the structure is cooled or annealed, a process I find similar to tempering chocolate because as temperature is lowered, the structure has less energy, and starts falling into a folded configuration. As for chocolate, well, when it is cooled, it starts to crystallize in specific ways, which prevents it from melting as quickly. I digress. Now, these folded structures can be further combined, as is done in the paper we're discussing, to make even more tailored and complex structures. As you can see, there's different ways in which this further self-assembly can happen with different types of bridges. While I am not sure which approach is used by the paper, perhaps the sticky ends, since I was not able to find information what linker may have been used, the review I got this figure from says that the linker approach has practical advantages in terms of tweaking the structure after its initial formation. And as a note, I'm only like 50. Okay, I'll bump that up to 60. I'm only 60% sure that these diagrams concern further self-assembly, like let's see. Like what is seen here, right? Like these are the same or similar structures to what we saw in figure 1 right here. Right, so I'm actually not 100% sure that the linker thing has anything to do with further self-assembly and not just the annealing process, but again, I digress. Now, the figures mean we actually have to look at the big scary polyhedron of mathematical doom. As you can see in figure 2, how this polyhedron is constructed is by separating the parameter space of things like individual bond strengths and particle concentrations by the space for which a specific structure can and can't form. Taking this to the limit, both mathematically and conceptually, we get a boundary of 0 yield and 100% yield. This is the crucial step, so let yourself marinate in it. Okay, done marinating, that's good. So after this is done for every single structure, we have a bunch of these boundaries separating the phase space, and when four of the innermost planes cross, that's what gives us the cone or polyhedron. For everything outside of this cone, no structures will form. This is the reason we cannot simply use different sides to form this polyhedron. It actually doesn't have to be 4 sides. As you can see here, it's like 5 sides. But again, I digress. The sides are important. Wait, what? Yeah, this is the no structures can form outside of the cone thing is why we cannot simply use different sides to form the polyhedron, as having a plane inside of it would violate this condition. The sides are important because they govern so-called designable structures, as I mentioned, one which can be made with 100% yield. If we set parameters directly on the faces of the polyhedron, we will get the corresponding structure at 100% yield. If we set parameters within the cone, then multiple structures will form. However, not all structures are so fortunate as to be designable, as evidenced by panel C. If there are planes which only intersect the cone at some point or line of points, then those structures can only be formed if the other structures corresponding to the other planes which the desired plane intersects are also formed. This is formalized in panel D with the help of a Hasse diagram or a Hasse diagram. I feel like it's German, so it's probably Hasse. I do not know German, by the way. To be honest, I have not seen a Hasse diagram ever before this paper. The closest I've gotten is neural network diagrams, so bear with me. But hey, that's what we're here to do. We're here to learn, and we're here to give me grace because I do not know what I'm talking about. Although the example of a polyhedron slash cone we have here was in three-dimensional space, right? This tiny inset right here is all you get. The intersections can have like 6, 7, really any number of necessary chimeras or co-occurring structures in a designable set. Where are the, okay, there are the Hasse diagrams. This means that for larger systems with more types of particles, oh, okay, I already said that. Sorry. What these Hasse diagrams do is classify these intersections by how much freedom we have to vary the parameters when making a certain designable set. Specifically, this freedom comes in how many dimensions the intersection has. For example, in figure 2, panel C, right, which we already saw, this intersection is one-dimensional, this pink line right here. If we wanted to design the rhombus, we would have to set the parameters along the pink line in this inset. It is theoretically possible then to have another plane intersect this line at only a single point. Therefore, it would be closer to the three-dimensional end, which is where all the planes meet at the origin, and hence, what? No, that's wrong. What am I saying? Okay, I'm sorry. Um, Yeah, then as evidenced by figure 3 panel B, therefore, yeah, it would be closer to the three-dimensional interior, which is where no structures form. This is as evidenced by figure 3 panel B, where the three-dimensional interior end is where all the planes meet at, or no, where none of the planes meet. Am I stupid? Who wrote this script? I'm sorry. Hence, all structures are present at the zero-dimensional end, but no structures are present at the three-dimensional end. There you go. That being said, I don't actually understand why the 3D interior corresponds to no structures forming, which should have been obvious. Basically, visually, the number of types of structures formed decreases as the dimension increases, but also the interior of the cone is where any structures may form. Perhaps it's something to do with 100% yield, however. But why would it be 100% yield? You can't have all the structures forming at 100% yield. Anyways, before moving on, I'll leave the rest of figure 3 up on the screen for you. It is interesting, but there's not much to discuss since it's the same ideas with different examples and binding rules. And this is just the polyhedral cone that was used in the Hasse diagram below. What am I? Okay. All right, home stretch. Figure 4 shows us the predicted and measured because yes, they did experiment with DNA origami. I didn't yap about it for nothing. Yields of these structures. Theoretically speaking, these yields are related to entropy and interestingly enough to the symmetry of these structures. This is also where the thing with almost any number of parameters I mentioned comes in. The gist of it is, while it is a goal to maximize the yield of a desired non-designable structure within a designable set, how far we can get with this is limited by geometry. Bear with me once again while I explain maths for the, okay, not the very first time in one of these videos, because I wrote this section of the script before I did for the theoretical paper, so it's not the first time that I'm explaining maths in one of these videos, but it's one of the first times I'm explaining maths in one of these videos. So there's these equations in the paper, equations 5 and 6, which honestly, let me just share my browser screen at this point. So yes, there's these equations 5 and 6. And what they state is the parameters we can tune for any given set fall into one of two categories, parallel or orthogonal. Parallel really does nothing for us here. Lambda is the parameter we take to infinity in order to say a structure is designable if it has 100% yield when lambda goes to infinity. The interesting part is the orthogonal component. This is exactly where we can vary exactly what we can vary in order to maximize the relative yield we need. That being said, as discussed around these equations and by common sense of what orthogonal means, the number of parameters we can vary is less than what one might expect. This is also discussed in the methods, and this is because, for example, for a one-dimensional intersection in 3D space, we may have only one parameter that we can vary. Actually, that isn't a very good example, but the gist of it is we might not have as much freedom to vary parameters as we might want. Oh, and back to the slideshow. Let's see. And for the experiment, they just counted. They used electron microscopes and they counted the structures to get the yield. I didn't talk about electron microscopes for sake of brevity and for the sake of my voice, but they're cool. Look them up and I'll link something about them if I don't forget. And in fact, electron microscopes is how these figures, these images on the right were obtained, and also how this smiley image was obtained. Isn't that cute? This is made of DNA back in 2006. Science is awesome. Anyways, on to the further questions. As I mentioned in the beginning, and this is for the what does this paper change section, as I mentioned in the beginning, most of the work going into this self-assembly research has been regarding finding the most optimal sets of binding rules to assemble specific structures. That being said, as this is the applications paper of this episode, I believe this kind of not obvious connection to mathematics, right, geometry perhaps, is important to discuss. It's also of intrinsic interest to me because, well, I like when math is pretty. In general, though, DNA origami has applications in material design, biochemistry, and of particular interest to me, specifically biophysics. These nanostructures can help us understand the microscopic structures within the body on a deeper level of abstraction, right? If you know that biology is an abstraction of chemistry, is an abstraction of physics, is an abstraction of mass chart. That's what I'm talking about when I mean abstraction. This can in turn have important applications in biomedicine, as noted in a review, which will be linked in the description. One of the directions for improvement that this paper mentions is lifting some of the constraints, such as the stiffness of bonds. The framework relied on the assumption that bonds were stiff and couldn't be strained, an assumption adopted by many works, or at least in this series, from what I can tell. The paper states that lifting this assumption could help in developing a more complete understanding, and of course, perfectly rigid bonds are a simplification. Also, much of this paper relied on the linear dependence of the interaction on various parameters such as particle concentrations and bond energies, and this is precisely what allowed us to define some singular parameter lambda to take to infinity to let us predict designability. And while a linear dependence is a fair assumption in most cases, it does translate to only local interactions, and non-local interactions are a cool direction which the research may develop. All right, I think that's it for this paper. The next paper talks about axion dark matter. As evidenced by the title, search for ultralight axion dark matter with a levitated ferromagnetic torsional oscillator by all these people. Unfortunately, that's a bit too many names for me to read, but I'll read the first two, I guess. Chunlong Li, Yue Huang, and Xian Yang, and the other people. So it's searching for dark matter, this paper. I swear it's complete coincidence that both this paper and the previous one were published on the 8th of January. Or I guess this one was received on the 8th of January. Anyways, axion dark matter searches fall into three main categories: coupling to photons, coupling to electrons, which is what this paper talks about, and coupling to gluons, which involves neutrons' electric dipole moment, which is small for reasons axions would be able to explain. Now, I want to clean up some terminology because this is terminology used throughout physics. So coupling here simply means interaction, how the axions interact with photons, electrons, gluons. On Earth, this research relies on comagnetometer data from a work cited in the paper we're talking about. I should come up with better terminology. Any suggestions? Because in interneting terms, we have OP for original poster. I think should I just adopt that OP for original paper? Yeah, let's go with that. I'm hip with the kids. So from Ref 58 in the OP, we have this diagram right here for the experimental setup of a co-magnetometer. The axion detection here relies on this field they form affecting only the helium atoms, which is a fair assumption for reasons I don't understand. Or maybe I do, since from what I can tell, these potassium atoms are affected by like this laser's polarization, while the helium isn't, which I guess is related to spin. That being said, I'm sure there's a deeper reason behind this, and I encourage you to look into the references in the OP if you want to. There's also solar axions, as you can see here, which, because they have to go through the space between the Earth and the Sun, are very cold, and some of the issues with thermal noise are alleviated, I think. It seems like the Earth's magnetic field also contributes somehow in their detection as well. Solar axions can be probed when considering axion couplings to photons, specifically photons with wavelengths in the X-ray regime, as evidenced by a paper published in CERN's CAST collaboration. Assuming I find it again, I will link it. So, what is an axion? Well, it's a lot of things. For the purposes of this paper, it's just a very light boson whose interactions are very weak in the magnitude sense, not in the weak force sense. However, depending on how they formed, they could be something called cosmic strings right here, which are like wrinkles slash topological defects in space-time. That's pretty cool. I think those would be considered more axion-like particles, though. As you can see, these strings are at the boundary where this parameter, I'm pretty sure this parameter has something to do with CP violation, which is something that axions attempt to solve. In any case, apparently quasi-particles can also behave like axions in the sense that their interaction with the electromagnetic field is axion-like, as evidenced by a paper published in April of 2025, and this is the news reporting. Also, while scripting this, I have realized I need to learn how to read because I was going to point out my confusion regarding how I thought axions could only occur in 2D systems. Turns out I was confusing them with anions. You can't make this up. Anyways, axion wind is the interaction between the axion field and the electromagnetic one. Specifically, it is the magnetic, or rather pseudomagnetic field, generated by the fact that the axion field oscillates. What does this oscillation mean, as in what is actually oscillating? Well, the field itself. Given a certain energy, this is quantum mechanics after all, this disturbance or oscillation in the field becomes a particle, an axion particle. That being said, it is important to remember the origins of this field when talking about oscillations. It was originally proposed as a way to solve the strong CP or charge parity problem, in that the strong force does not violate CP symmetry, even though nothing in the theory prevents this. This is because the factor of the CP violating part of the model, of the standard model, or I guess of quantum chromodynamics, which is a strong force part, is very small. Where the axion comes in is this factor basically becomes a field instead of some presumably external, as in the theory doesn't predict it, number. So effectively, as it stabilizes to this very small value, it overshoots and undershoots, behaving a bit like a pendulum. This can also be seen in this diagram showing axions as cosmic strings. Here, I'm pretty sure this thing right here would correspond to the CP violating factor even though this is not the notation I'm familiar with, but sure, let's just take it. Um, I think even if it's not the case, it might be a helpful tool in understanding. These axions would exist at the boundaries and effectively, I'm not sure if they would mediate, but yeah, in any case, they would take, depending on how much axion dark matter there is in a specific place, maybe CP violation not would occur, like theoretically. I'm not sure. I'm not sure because this is very confusing conceptually. Even to me, because this field represents a parameter of the theory, so how does that translate into physical matter? But you know what? Electromagnetism, that's the part that matters. Axion wind gives a pseudomagnetic field that then becomes an actual magnetic field through experimental magic. Source for the experimental magic will also be linked in the description. Wow, I am promising y'all a lot of things. The gist of it, from what I can gather, is pseudomagnetic field interacts or couples to the electrons, and in turn, the electron's behavior is what generates an actual magnetic field. Oh, this is the slide for the strong CP problem. Nice, I should have scrolled to it. Yeah, but these are some of the foundational papers, or I'm not sure how foundational they were. They were linked by Wikipedia. In basically proposing or asking if axions may be able to solve the strong CP problem. Anyways, in the same paper that helped me understand the pseudomagnetic field thingy, there's also a mention of shielding. In short, as stated in the OP, certain types of shielding can block out the axion wind itself. This is why in the OP there's a section for shielding attenuation and a different sensitivity for when this shielding is considered. There really isn't anything special to discuss. Axion wind is mostly just another magnetic field, even if there's some steps to get there. And the shielding doesn't care where the magnetic field comes from, it blocks everything. So there's that. Yeah, as you can see, shielding is kind of different, right? For shielding, the magnetic field is bended. For screening, there's just something in front of it, basically. And for cloaking, the field outside does not get bended, but the field inside is non-existent because the material bends the field within itself. Also, perhaps way less advanced than what I just talked about, but I think it would be fun to talk a bit about ferromagnetism. So, how the different magnetisms are defined is actually a bit confusing. There's ferro and ferrimagnetism, which I'm surprised I didn't typo in my script, and the difference here is the alignment of the spins. Ferro is all in the same direction, while ferrimagnetism is where most of the spins are in the same direction, but not all. And the blue here indicates that the the down spins are less prevalent or perhaps less strong than the up spins. So the overall magnetism, loosely speaking, will be weaker. There are also para and diamagnetism. Those aren't really important, they're never mentioned, but the difference there is whether they are attracted or repelled by magnetic fields. How and why? Beyond the scope of this video and my knowledge. Okay, thanks. Anyways, figure 1 illustrates the experimental setup. The entire setup is protected from the outside magnetic noise by a magnetic shield, since it doesn't really matter that if the outside field is going to be distorted, we can use a shield instead of a cloak. Again, it's just super technical details. You don't really need to understand them. And a vacuum chamber also surrounds the whole setup. The levitated magnet's movement is measured with the help of a laser, a camera, and a mirror setup. Depending on how the magnet rotates, the mirror will also rotate slightly, hence deflecting the laser differently. The camera picks this up and calculates the actual motion from this data, which is then used to determine the potential values and set limits on the coupling constants. There's also these coils which calibrate the particles inside the magnet to point their spins in a particular direction, kind of like what is done here with the laser. And let's see, and any deflection of these spins would cause the magnet to rotate slightly. This is the basis of the experiment, and because the magnet is levitating, nothing resists its rotation. Figure 2 and 3 are power spectrum distributions. These aren't anything scary. They're related to Fourier transforms and give us a way to visualize the frequencies which we need to add together to approximate the function. I realize a lot of this episode has been related to Fourier transforms. The first theoretical paper, then this paper, and also the last paper has something to do with the Galerkin scheme again. It's Fourier themed, okay? It's Fourier themed. Anyways, what figure 2 shows is the experimental data acquired by the setup used. It is data on the magnetic frequencies obtained graphed against the power of each of the frequencies. You will notice the distribution is quite spiky. I think what this is saying is the detector is less sensitive to frequencies which are farther from the resonant frequency in the middle. Now, why do I believe this? Is because, full disclosure, I did not know about PSDs before reading this paper. It's because the deal with resonant frequencies, right, is they produce the most motion. For example, here it's rotational motion. So even with less of the frequency, less power, you would still get the same amount of motion is what I'm getting. Hence, it's not really the fact that the detector is more sensitive. It's just that the system responds more to the resonant frequencies. Note that we did not know this resonant frequency before this data was gathered, as is evidenced by table 1, which I'm not going to show. Sorry, go look in the paper itself. The magnetic PSD mentioned in the description to table 1 is precisely the one we're looking at in figure 2. But again, that doesn't really matter. Um, so yeah, a similar approach can be taken to understanding figure 3. While I'm not sure how to interpret this slight dip as a resonant frequency here, in terms of reading the graph, it's the exact same thing. The coupling constant should have some value depending on the mass of the hypothetical axion. And this GAEE, can I laugh? Depends on the mass, on this hypothetical axion mass. Also, bringing back something from the test run where I was confused about the CL thing, right after publishing that video, I figured out it meant confidence level, which is just a historical blunder for me. Anyways, yeah. Well, let's see where I left off. This figure sets a confidence limit on this coupling constant given this mass. And from what I can tell, this basically means if someone were to find a signal within these parameters, they would have found the axion, I think. Don't quote me on that. Anyways, further questions. What does this paper change? Well, if you're a returning viewer, you may already know where I'm going with this. After the micromoon paper from November of 2025 ruled out a significant chunk of sterile neutrinos, physicists have been having to adapt to new theories of dark matter, of which axions are pretty prevalent, especially considering they also solve another long-standing problem in particle physics, that being the strong CP or charge parity problem, which I talked about earlier. So this paper opens up a new avenue through a new experimental setup to potentially detect axions. It's like the more things you throw at a wall, the higher the probability something will stick. That being said, this paper did not find axions. It really couldn't have, since the sensitivity of the experiment for now is not very good, as evidenced by what? Come on, I had it somewhere. Yeah, as evidenced by this thing right here. Right, this is the sensitivity of our experiment here. This is the sensitivity of old co-magnetometers, which have already been studied extensively. This is for solar axions. That being said, as you can see at the bottom here, if we reduce the temperature significantly, then this experimental setup could potentially give us even more sensitivity than red giants, which is a whole nother ballpark for axion detection experiments. And even just at 4 Kelvin, we would have the same sensitivity as solar axions right at home on Earth, which is like so cool. Anyways, the sensitivity falls again within the region, which was already analyzed. And there are also specific paths for improvements, which are devised in accordance to the limits set by this paper for the coupling of axions to electrons. I'm also in with the times, as you can see, by the fact that I put a meme here. All right, final paper, we almost made it. Thick lunar crust amplifies gravitational wave signal by Lei Zhang, Han Yan, Xian Cheng, and Jinhai Zhang. So I think the best way to start out the summary is to point out that this paper contains the phrasing of calibrating the moon. However, this is not because it proposes a large-scale change of the moon for our own purposes. We're not going to steal the moon, unfortunately, but it instead studies how the moon's existing structure could amplify and help us detect gravitational waves. The paper justifies this approach with the fact that the moon is quiet compared to Earth, not only in terms of the fact that there are no people there, but it's also quiet seismically, which means there will be less noise in any measurements of how gravitational waves cause some seismic effects on the moon and are in turn amplified, right? The gravitational waves are amplified, but I'm getting ahead of myself. As you may know, the moon has many peaks and valleys, as shown in this paper. Unlike the scientifically proven Kansas paper in the description, it is not flatter than a pancake. Before this paper, there were already proposals of using the moon as a tool to measure gravitational waves. Yeah, okay, not there. Not on that slide. However, the moon was being modeled as a sphere, which, as shown by this paper, is not a very good approximation. This is because the peaks and valleys, or the variation in crust thickness, actually contributes significantly to the amplification of gravitational waves. The paper analyzes this using two separate approaches: an analytical perturbation theory approach and a computational spectral element method (SEM) approach. The former relies on the previous research where the moon was approximated as a sphere, like how a cow might be. You don't say. And adds the actual topographical details of the moon's surface into the theory as perturbations. This theory gives us the modes at which the moon's surface will oscillate. However, these are mostly not kinetic oscillations, they're potential energy oscillations, and the theory also takes into account the fact that at different depths, the moon's crust may respond differently to the gravitational waves, and this is encoded by the shear modulus. The latter SEM approach basically ran a full 2D simulation using the topographical data, modeling how the moon responds to gravitational waves, thereby amplifying them. Before we start, I want to talk a bit about a bit. Why did I don't have a Slavic accent? Why did I say a bit? I want to talk a bit about gravitational waves. As you may know, the first gravitational waves were detected back in 2016 by the LIGO Observatory alongside the Virgo Observatory. Why? Why do all these people have the last name Abbott? Why do both of these have the last name Adams? That's so cool. That's so interesting. Anyways, um, fascinatingly enough, these results were announced on my birthday in 2016, which is pretty neat. Again, shameless engagement bait. In any case, since then, science has been very much chasing that high, and many gravitational wave detectors, as noted by the paper, right, like LISA from NASA and Tianqi and Taichi in China, are in development. But the point of this paper is, after all, the moon. And that is because in order to detect gravitational waves, we needed very large distances, which is something that setting up on the moon, as for example, like Lila or Taichin or Taiji could provide us. The reason we need these large distances is because gravitational waves are very, very weak at earthly scales. According to Wikipedia, this would require, or this did require, the precision on the level of zeptometers. You haven't even heard of that unit, but it's 10 to the negative 21 meters, 1/60th of a meter. And even the detection at LIGO alongside Virgo was very, very weak. That being said, it was conclusive to have a Wikipedia page, so, good enough. Next, I would like to talk about the numerical methods used by previous papers by these authors, specifically the spectral element method. What this method does is it breaks down a multidimensional problem into smaller building blocks, effectively modeling, say, a sphere as a series of many point particles. In this method, a sort of mesh is drawn over whatever object we want to analyze, and every point in this mesh is allowed to move in some way as described by the differential equation we're trying to solve. For the case of the moon, this method translates the overall force generated by the gravitational wave into how it acts on these individual mesh elements. And fascinatingly enough, the details of this method include a callback to the very first paper we discussed, as I mentioned, with the Galerkin method. The general concept is the same, effectively fitting the solution to the equations. However, the SEM method specifically uses polynomials, or rather piecewise polynomials, basically so that the slopes at every point can be fine-tuned. And there's probably other mathematical quirks I'm not aware of. The important thing to note about the application of this method in the paper is that only a great circle of the moon has been analyzed. The authors pointed out that a 3D analysis would be too computationally expensive, even with the insane specs of the supercomputer they used. Like, I'm pretty sure it was something like 512 gigabytes of RAM per like cluster. My brain barely has that much memory. Anyways, the other approach used is in this paper is perturbation theory. To reiterate, what this paper did is take the model of the moon based off the assumption that it is a perfect sphere. This is articulated as spherical or spherically symmetric, non-rotating, elastic, and isotropic, aka not having any variations throughout the paper. And then apply any actual variations, such as in crust thickness or in shear modulus, effectively how much force a particular layer can absorb before it starts moving, and it applies all these parameters as perturbations. Now, if you'll indulge me, I want to go a bit into the maths of this. Basically, to derive the amplification ratios, which is what this theory derives for us in this paper, a certain set of eigenmodes of oscillations are modified, and these are this k vector. This k vector, yeah. There's 4 of these for the like perfect spherical moon, right? These SNREI moon. These new eigenmodes are expressed in terms of the old ones because, being perturbation theory, the displacements are small. A cool technique used in actually calculating what these combinations would be is called Woodhouse kernels. Basically, this is a technique that breaks down complicated problems involving integrals by separating out as much dependence as possible. In this case, first separating angular and radial components, and then separating kinetic and potential energy functions, which is how the eigenmodes are derived, as you can see here. V is the potential energy operator, T is the kinetic energy operator. And Woodhouse kernels separate these by various variables that they depend on. This analysis was performed on a full 3D model of the moon, the perturbation theory analysis, which gives a fuller understanding, right? This thing right here isn't part of the perturbation theory analysis. I only put it up so you could see the crustal thickness variations, which relates. And this meme right here is basically poking at the equation. That's basically what perturbation theory does. It adds small variations. Anyways, lastly, a common theme throughout the series of papers that OP belongs to is to average across all possible directions that the gravitational wave can be coming from. By averaging this, we get a clearer picture of how different structures respond to gravitational waves overall, rather than just for a specific direction, and you will see this figure later as well. All right. So figure 1 shows us the lunar topography data that was used by this study. Panel A shows the full map of the whole lunar surface, with blue regions representing thicker crust and red regions representing thinner crust, while panel C shows a cross-section of only the great circle that was studied, right? Studied by the SEM theory, by the SEM method. SEM method is a redundant abbreviation because it's spectral element method. CHI-T. As justified in the paper, the specific great circle is chosen because it has a variety of defining features. The South Pole Aitken, I probably butchered that, basin, as well as 2 mares or regions of thin crust. This line on figure A represents this great circle. And it is curved because, for the same reason that airplane paths are curved on a flat map, because the map is flat, the moon isn't flat. Are there any flat mooners? Because I know there's flat earthers, but does anybody think the moon is flat? I have to look into that. I hope not. As for panel B, I have been purposely avoiding it because honestly, I wish I could tell you what the L means throughout this paper. And this is probably going to be like one of those confidence levels things. confidence level things like with the previous episode. But anyways, from this figure, it's likely a measure of how much detail is used, since, for example, some of the mares on the left are not shown as clearly on this panel as panel A. That being said, L is also used to describe the oscillation modes of the moon, with the quadrupole mode shown, for example, in panel D. Let's see, panel D, did I put that up? All right, hold on. In panel D, in panel D, in panel D. Hold on, let me pause real quick. Anyways, this um this is the quadrupole mode shown, and it was also shown in the presentation, but whatever. This is basically just, well, quadro means four in Latin. Presumably, this is from Latin, not from Spanish. But yeah, this is approximately how the moon will respond. It's not actually how the moon will respond because it's not going to bend that much. These are vectors. Anyways, back to the presentation. I hope I don't show something that I don't want to show. Anyways, yeah, the quadrupole mode of oscillation. So while this is a complete guess, it may be possible that L equals 4 here has something to do with the fact there's four levels of lines, right? At 50, 40, 30, and 20 kilometers of thickness. Next up is figure 2, which shows details of the SAM simulation of how seismic effects, which uh, gravitational waves create, are formed and how they propagate, right? A comparison between the spherical model and this paper's model is given at a short time after the gravitational well, a short time after a short time after a gravitational wave is felt, and at a relatively long time. T is equal to 100 seconds and T is equal to 3,000 seconds for panels A, B, and C, D, respectively. It shows the velocity, blue meaning outwards and red meaning inwards, of various regions in this cross-section great circle of the moon. Really, it's a cross-section because you see the inside of it too. As you can see, there is still some agreement between how this phenomenon evolves, specifically with panels C and D. The highest outwards velocity is roughly in the same place. That being said, it is higher than in the spherical model, and this corresponds to the fact that the thicker crust regions are roughly in the same spot. Well, kinda. The left and top regions aren't notably thick, right? Like right here. Let me draw. Like these regions aren't notably thick, but they still have significant outwards velocity, as well as like honestly this region too. This is literally the spot basin. Anyways, let me just clear this. I'm pretty sure that this fact that the thinner crust regions also have a relatively high velocity is just due to correspondence with the spherical model, though. And panel E quantifies these observations by comparing the crust thickness outline with how much the gravitational wave actually affects the crust velocity, effectively how much it is amplified. Figure F builds on this to show which frequencies of gravitational wave get amplified the most by which places on the moon. This is the angle, right? It's very small, but this is the angle. And this is also the angle. So basically where on this great circle, it is amplified the most. And we can see that the strongest amplifications happen at around 15 megahertz, 12.5 megahertz, and at 20 megahertz less so. Figure 3 is the last one in the main text, right here on the right, and it shows something very similar, except for a 3D map, because this was derived with the perturbation theory. Now, if you overlay the great circle path from figure 1 on the bottom right here, you will get good agreement to the figure 2E panel. In this figure, we have the amplification ratios, and this shows that thicker crust amplifies more, which is basically the point of this paper, right? And thicker crust amplifies more because it is affected more by gravitational waves. Panel B again mentions that L thing I was confused about, but really I don't think the specifics matter here. Like it's just some kind of contribution. Specifically, the kind of contribution which was important for the earliest spherical models, per the paper's own words. Assuming spherical symmetry, earlier analytical works established that only the moon's quadrupole L equals 2 mode resonates with the GW, with the gravitational waves. And again, this is per the paper's own words. The figures in the appendix show some experimental details. Let me just switch back to that again. These figures show some of the experimental details, what frequencies of gravitational waves were tested. This is panel E, right? The source time function. Huh? Is this wrong? The normalized amplitude. Okay. Oh, never mind. The source time function with a duration of 5,000 seconds, and this basically shows when the gravitational wave gets applied, I think. I think so. Yeah, I think so. And in figure A2, we have that averaging thing I told you about, right? Testing a bunch of different, in this case, polarizations to get a more accurate idea of the overall response. Back to the presentation we go. Further questions, what does this paper change? So this series of papers is absolutely foundational in future gravitational wave technologies because we have LIGO and Virgo, and they're already really good. And what scientists are looking into now is putting a detector on the moon. Fascinating stuff. So the hope is that as the seismic signatures are understood, we will be able to detect gravitational waves and the astronomical effects which produce them at scales which Earth-based detectors have prohibited. Because as you may remember, the LIGO paper detected gravitational waves from a binary black hole merger, which is a very, very strong event. One of the strongest in the entire universe, right? Black holes are already like some of the most cool stuff, cool things in the universe. So anyways, but hopefully putting a detector on the moon, which again, I want you to marinate in how absurd that sounds and how cool that sounds and how much science is doing. Can you tell I'm excited about this? I'm very excited about this. I don't know why I said this was going to be the out of my niche paper because I'm so excited about this. Yeah. All right, so like LIGO detector still is already very good, as I mentioned, on the level of zeptometers. You don't even know what that unit of measurement is, and that's okay. I didn't know what it was before this video either. But from what we saw in this paper, let me zoom in really quick. The seismic effects are on the order of 10 to the negative 15, as opposed to 10 to the negative 21 meters per second, right? That was meters, this is meters per second, but like that's 6 orders of magnitude, which is so promising. Anyways, aside from the applications, this paper states very clearly what is to be done, a full 3D SEM simulation. However, I'm not sure how feasible this is with current capabilities. Theoretically, anything is possible. It'd just take a lot of time, but of course, that brings in the question of if anyone would let them. Please give the scientists computers. Please let the scientists play with supercomputers. It'd be really cool. In any case, a further question I personally have is, for example, for Leela's experimental setup, which is putting a detector on the moon, how the moon's seismic effects, or no, how the moon's presence would affect any detections on Earth. Of course, there's much more pressing issues, such as seismic effects on Earth and how to get the detectors on the moon. That feels like a much more pressing issue than what I'm about to bring up here. But the entire premise of this question is self-indulgent, so, I just think it could be interesting to either read through or even work through, if I knew what I was doing, some of the maths related to how the moon being in the way might affect gravitational wave detection on Earth. Probably not a lot, right? Realistically, not a lot, simply because gravitational waves tend to pass right through things, but again, self-indulgent. And as a final note, especially what I found insightful with this paper is the use of operators, right? Does it mention it as an operator? I'm not sure if it mentions it as an operator here, but it is called an operator, which I find fascinating because operators in my head have always been allocated to quantum mechanics, and it's cool to see how mathematical principles from many different fields can interact and overall make a better theory. I don't know. I just think that's so cool. All right. And matter time. Now that everyone who wants to leave has left, I can discuss some end matter. Firstly, if you have papers you want me to read and talk about, comment them. Comment the DOIs, and I might read them in the next video. Funny thing about this is I turned on subtitles for my previous physics recap video, and it transcribed DOI as DUI. You know, I don't know. I think that's funny. Um, Anyways, commenting should work logistically considering these videos come out around midway through the month. So the February episode would come out like midway through March, so it should be fine. However, whether I cover them and in which slot of the format they go in is completely up to my discretion. So if one of your papers goes into the last slot, I'm sorry. It just wasn't very interesting to me. But again, we are here to learn. And if your paper can force me to learn something, then that's just as cool as you getting my personality right, honestly. Second, I'm doing content for a science magazine now. It's called Interstellar Magazine, and I'll link them in the description. Go show them some love since the only reason I got on there is to get them a social media presence. So it'd be really cool if you could show them some love and read some of the papers, some of the um, issues that they're publishing. It is youth-led, I think. It's youth-led. It is, and it focuses on the intersection between scientific fields, kind of like what the applications paper I talked about does. Yeah. Also, happy Valentine's Day again. Sorry I was mean to you in the intro. I was projecting. Lastly, I'm working on something of a passion project, also related to physics, so look out for that. And by that I do mean please subscribe because it'd make me really, really happy, even if it's a complete long shot, if I could get 50 subscribers before April 1st, because I want to do an April Fool's stream the where I read some Arxiv articles, some Arxiv April Fool's articles because Arxiv is really nice to let people submit their April Fool's articles. But if not, that's okay. I have made a Twitch, so like it's whatever. All right, I will see you next time. Thank you for watching. I hope this was fun. I hope this was informative, and I am once again sorry for roasting you. All right, see you next time.